Hello students, have you ever noticed how the same convex lens can act as a projector, a camera, a microscope, or even a magnifying glass? It sounds almost magical, doesn't it? But really, there's no magic here, just physics at work. So how does one lens pull off so many jobs? Well, the secret lies in the position of the object. Depending on where you place the object in front of the lens, the image can change completely. Here's the cool part: a convex lens can form images that are real or virtual, inverted or upright, magnified or diminished. In other words, this lens is like a shapeshifter, always following the rules but changing its behavior based on the object's distance. Think about it: in a projector, the object, the film or slide, is kept just beyond twice the focal length and the image becomes large and real on the screen. In a camera, the lens adjusts so that the object forms a tiny, sharp, inverted image on the sensor or film. In a microscope, the object is kept very close to the lens, creating a highly magnified virtual image. And as a magnifying glass, you've probably used it to make words in a book look bigger. That's just a convex lens at work again. Today, we'll explore each of these cases step by step. We'll use ray diagrams to see how the image is formed and the lens formula to confirm the position and size of the image mathematically. So, get ready. By the end of this, you'll not only understand why a single convex lens can do so much, but you'll also be able to predict exactly what kind of image it will form in any situation. Alright students, let's start with the simplest case: what happens when the object is at infinity? Now, infinity sounds scary, but in optics it just means very, very far away. Think of the sun, for example. Light rays coming from such a distant object are practically parallel to the principal axis when they reach the lens. Here's the magic: when these parallel rays pass through a convex lens, they all converge at the principal focus F on the other side. No guessing, no randomness, they always meet right there at the focus. What kind of image do we get? Since all those rays squeeze into a single sharp point, the image is real, inverted, and highly diminished. In fact, an entire huge object like the sun gets reduced to a tiny bright spot at the focus. Imagine fitting the sun in the palm of your hand. Optics makes that possible on a screen. And yes, this has a very cool application. If you've ever tried projecting the image of the sun on a screen using a magnifying glass, that bright, tiny dot you saw is exactly this principle at work. But a safety reminder: never look at the sun directly through the lens unless you want your eye to become a physics experiment. So, to summarize, when the object is at infinity, the rays are parallel, they meet at the focus, and the image is small, real, and inverted. A perfect starting case before we move objects closer to the lens. Now students, let's bring the object a little closer, but still far enough. Suppose we place it beyond twice the focal length, or 2f in front of a convex lens. What happens? The rays from the object pass through the lens and come together on the other side. The image doesn't form too far away. Instead, it appears between f and 2f on the other side of the lens. Let's check the nature of this image. It is real because the rays actually meet, inverted because it flips upside down, and diminished because it's smaller than the object. So, you get a neat, reduced copy of the original. Here's a real-life connection. This is exactly how cameras capture distant objects. Think about when you take a photo of a tall building. The entire building, far larger than your camera, gets reduced to a tiny, sharp image on the camera's sensor or film. The lens is doing the shrinking for you. So to summarize, object beyond 2f gives you a smaller, real, and inverted image between f and 2f. In other words, The convex lens acts like a natural photoreducer. Okay students, now let's place the object exactly at 2f or twice the focal length in front of a convex lens. What do you think will happen? Here's the result. The image forms exactly at 2f on the other side of the lens. No surprises here, the distances balance out perfectly. And let's check the nature of this image. It is real because the rays actually meet, inverted because it flips upside down, and most importantly, it is equal in size to the object. Not smaller, not bigger, just the same. This principle is actually put to use in photocopiers. When you place a page in a photocopy machine, the lens system forms a same-sized, inverted, real image of the text, which is then processed to give you an identical copy. Imagine if the copier lens got it wrong. One day your homework might come out giant-sized, and the next day, too tiny to read. So, the takeaway here, object at 2f gives image at 2f real, inverted, and equal in size. Simple, symmetric, and super useful in everyday machines. Now students, let's move our object a bit closer, this time placing it between the focus f and twice the focal length 2f. What happens here is quite interesting. The rays from the object pass through the convex lens and meet beyond 2f on the other side. Now, let's check the nature of the image. It is real because the rays actually meet. It is inverted because once again it flips upside down. But here's the exciting part, it is magnified. The image is bigger than the object. This principle is put to powerful use in projectors and microscopes. In a projector, a small slide of film is placed between f and 2f and the lens produces a large image on the distant screen. That's why you can watch a full movie on a big wall, even though the film reel itself is tiny. Similarly, in a microscope, placing the specimen close to the lens magnifies it, letting us study details invisible to the naked eye. So to summarize, an object between f and 2f forms an image beyond 2f which is real, inverted, and magnified. It's this case that makes lenses so useful for enlarging things, from tiny cells under a microscope to a big cinema experience on the screen. Alright students, let's wrap up with two very special cases for a convex lens. Case 1. Object at focus f. What happens if we place the object exactly at the focal point? The rays, after refraction, don't meet anywhere nearby, instead, they travel out parallel to each other. And when rays are parallel, the image forms at infinity. So in simple words, place your object at the focus and the lens says, sorry, your image has gone off to infinity. This is why lenses can produce collimated beams, used in searchlights, telescopes, and even laser focusing systems. Case 2. Object between O and F. Now here's the really exciting one. Place the object between the optical center O and the focus F. In this case, the rays spread out after refraction, but if we trace them backward, they appear to meet behind the lens. That gives us a virtual, erect, and magnified image. This is exactly how magnifying glasses work. You've probably used one to make a page of text look huge. It doesn't create a real image you can catch on a screen, but your eyes see an enlarged, upright version. Reading glasses, too, rely on the same principle. So to summarize, at F, the image is at infinity. Between O and F, the image is virtual, upright, and magnified. And these are the cases that make convex lenses not just scientific tools, but also everyday helpers, from reading books to exploring the stars. Alright students, let's do a quick recap of all the image positions formed by a convex lens. Think of this as the cheat sheet for every exam question and ray diagram you'll ever face. Case 1. Object at infinity. The rays come in parallel and meet at the focus. The image is real, inverted, and highly diminished. Just like the tiny bright spot of the sun's image you can project with a lens. Case 2. Object beyond 2f. The image forms between f and 2f. It's real, inverted, and smaller than the object. This is how cameras shrink tall buildings into a neat photograph. Case 3. Object at 2f. The image also forms at 2f on the other side. It's real, inverted, and equal in size. This is the principle behind photocopiers making a same-sized copy of a page. Case 4. Object between f and 2f. Now the image shifts beyond 2f. This time it's real, inverted, and magnified. Think of projectors. A tiny slide becomes a huge cinema screen image. Case 5. Object at f. The rays after refraction go parallel, so the image forms at infinity. This principle is used in searchlights and telescopes to create long, parallel beams. Case 6. Object between O and F. Here comes the special one. The rays diverge but appear to meet behind the lens, forming a virtual, erect, and magnified image. This is exactly how a magnifying glass makes small text look bigger. So, the big takeaway: a single convex lens is like a multi-talented performer, sometimes reducing, sometimes enlarging, sometimes flipping upside down, and sometimes keeping things upright. The key is simply where you place the object.